Hey everyone, tonight we're going back. Not a few centuries, not a few millennia, but 12,800 years, to a moment that changed everything, that nobody fully understands, and that left its mark in ice and rock and bone, and possibly in the oldest stories the human race has ever told, the Younger Dryas, a climate event so sudden and so severe that when scientists first discovered it in the evidence, we thought they had made a mistake. Before we begin, take a moment to subscribe, but only if you genuinely enjoy what I do here, and drop a comment telling me where in the world you're listening from and what time it is for you. Now dim the lights, get comfortable, and let's ease into tonight's journey together. Imagine standing on a grassland 12,800 years ago. The air is crisp but bearable. Mammoths move in slow herds across valleys that stretch to the horizon. Saber-toothed cats prowl the edges of the tree line. Above you, the ice sheets that once covered half the planet are retreating northward. You can hear water everywhere, rivers swollen with meltwater, lakes forming in valleys where glaciers stood just a few generations before. The world is warming. The long nightmare of the Ice Age is finally ending. For thousands of years, the warming has been steady, dramatic, unmistakable. Human populations are expanding into territories that were locked under ice for millennia. In the Levant, communities are experimenting with something that looks like agriculture. In North America, the Clovis people are spreading across a continent that is opening up before them like a gift. The future looks promising. Every trend is pointing in the same direction. Warmer, greener, more alive, and then everything stopped. Global temperatures plummeted. Not over centuries, not even over decades. In some regions, scientists believe the shift happened so rapidly that conventional climate models struggle to explain it. The glaciers that had been steadily retreating suddenly surged forward. Ice sheets that were supposed to be dying began to grow. We're talking about temperature drops of up to 15 degrees Celsius in some areas. In geological terms, it happened overnight. This period is called the Younger Dryas, and it is one of the most puzzling climate events in Earth's recent history. For over 1,000 years, the planet was thrust back into near glacial conditions at precisely the moment it should have been warming. And the question that still keeps scientists awake at night, 12,800 years later, is simply, why? Our three companions tonight are drawn from three different corners of this story. There is Alexa, a paleoclimatologist who has spent 15 years drilling ice cores in Greenland, and who reads the ancient atmosphere the way a musician reads a score, with attention to every small variation, every unexpected note. There is Devora, an archaeologist working at a site in the Levant, where the evidence of an ancient community disrupted by exactly this event is preserved in layers of ash and dried mud. And there is Thomas, a theoretical geologist who specializes in the intersection of ocean circulation and climate, and who has been arguing for 2 decades that the answer to the Younger Dryas question is hiding not in the sky but in the sea. All three of them are, in their different ways, trying to understand the same moment, the night the world changed. To understand what went wrong, you first have to understand what was going right. Because 14,700 years ago, at the beginning of what scientists call the Berling-Allerud interstadial, the warm period that preceded the Younger Dryas, the Earth was experiencing something genuinely extraordinary. Temperatures in some regions had jumped by as much as 8 degrees Celsius in just a few decades. Glaciers that had stood unmoved for millennia were retreating northward, at rates of up to 1 kilometre per year. You could watch the world transform within a single human lifetime. The ice sheets covering North America and Europe weren't just melting, they were collapsing. As they retreated, they revealed land that hadn't seen sunlight in 100,000 years, and life exploded into these new territories with an enthusiasm that is difficult to comprehend. Within decades, not centuries, tundra grasslands were spreading across former ice fields, rich, productive environments that scientists now call the mammoth steppe. Grass as far as you could see, thick and nutritious, supporting biomass densities that would make a modern savanna envious. The megafauna thrived in this world. Woolly mammoths moved in herds that numbered in the thousands, following the expanding grasslands northward. Giant ground sloths, some standing 4 meters tall, browsed in forests that were advancing steadily across former permafrost. Enormous bison, 25% larger than modern species, grazed alongside wild horses and, this still surprises people, camels, which were native to North America before they vanished, and massive elk with antlers spanning 3.5 meters. Predators followed the herds, saber-toothed cats, dire wolves, American lions larger than any cat alive today. And humans were right there in the middle of it all, adapting faster than anyone. The Clovis people of North America had developed hunting technologies that were genuinely revolutionary. The distinctive fluted spear points were not crude survival tools, but precision instruments, engineered with a channel that made them easier to haft and more aerodynamic when thrown. The Clovis culture spread from coast to coast in perhaps 500 years, following megafauna herds and the opportunities that the warming climate was opening. In the Levant, the Natufian people were doing something that would change human history forever. They were settling down, building permanent structures with stone foundations, experimenting with wild cereals that would eventually become wheat and barley. Everything pointed toward continued warming, continued expansion, a world that was finally becoming hospitable after 100,000 years of cold. Devora thinks about these people often. She excavates their traces every season, the plastered floors, the storage pits, the grinding stones, and she has spent enough time with these remnants of their daily lives to feel something that goes beyond professional interest. These were people who believed, with every reason to believe, that the world was getting better. They had spent their entire lives watching it improve. Their grandparents had watched it improve. Their communities were growing. Their technologies were advancing. Their horizons were expanding. And they were wrong, in the most complete and sudden way possible. The scientists who first discovered the Younger Dryas didn't understand what they were looking at. They were studying pollen samples from Scandinavian bogs in the early 20th century, building a timeline of plant life after the last ice age. The sequence made perfect sense at first. Arctic plants being replaced by temperate species, birch and pine appearing in layers that had been dominated by tundra vegetation. The progression orderly and exactly what you would expect from a world warming out of an ice age. Then they hit a layer that shouldn't exist. Right in the middle of the warming sequence, Arctic plants suddenly came back. Not gradually, not as a minor fluctuation, but as a complete reversal. The pollen of Dryas octopetala, a small white flower that only grows in the coldest conditions, reappeared in massive quantities in sediment layers dated to around 12,800 years ago. It was as if someone had rewound the climate by 10,000 years and then pressed play again. They called it the Younger Dryas, Younger because there had been older cold periods during the deglaciation, but none as severe or as strange as this one. When ice core analysis became sophisticated enough to measure past temperatures with real precision, the true scale of the Younger Dryas revealed itself. Greenland ice cores showed temperature drops of up to 10 degrees Celsius in the North Atlantic region. But it was the speed that made scientists check their data again and again. Some cores suggested the cooling happened in less than a decade, possibly less than 3 years. Some interpretations suggest it could have happened within a single season. Imagine being a human living through that. Your grandparents' stories about endless ice would have seemed like ancient history. The world had been warming for over 1,000 years. Every generation for 50 generations had seen the ice retreat a little further, the seasons become a little more forgiving. Then, in the space of perhaps a decade, possibly less, winter stopped ending. Spring came late, then later, then barely came at all. The glaciers that had been retreating for more than 1,000 years stopped. Then they started advancing again. The Younger Dryas was not just cold, it was drought, disruption, and a fundamental reorganization of everything. In the Middle East, the Natufian settlements that had been experimenting with agriculture faced severe drought conditions. The wild cereals they had been cultivating failed. Some communities simply disappeared from the archaeological record. Others abandoned their permanent structures and returned to nomadic life. In Asia, monsoon patterns shifted dramatically. In caves in China, the archaeological record shows sudden population collapse, not gradual decline, but rapid abandonment of sites that had been continuously occupied since before the warming began. This was not a regional cold snap. This was a planetary climate reorganization happening at a speed that, by the known physics of the climate system, should not have been possible. The Younger Dryas lasted approximately 1,200 years, roughly 60 human generations. Then, just as abruptly as it began, it ended. Around 11,600 years ago, temperatures shot back up, and the Greenland ice cores show that the warming at the end may have been even faster than the initial cooling. Within decades, possibly less, the climate system lurched back toward warmth. The glaciers began their final retreat. The forests started their northward march again. The Younger Dryas was over, but it left behind questions that remain, 12,000 years later, unanswered. The ice remembers everything. Every snowfall that landed on Greenland for the past 120,000 years is still there, compressed into layers like pages in a book written in frozen water. The trick is learning to read it. You fly to the middle of the Greenland ice sheet, to a place where nothing exists except white in every direction. You set up a drilling rig and start boring down through kilometers of ice, pulling up cylinders 4 inches wide, section by section, going deeper into the past with every meter. Each year's snowfall creates a visible layer, darker in winter when dust settles on the ice, lighter in summer when cleaner snow accumulates. You can count these layers like tree rings. 1 year, 10 years, 1,000 years. But as you go deeper, the weight of the ice above compresses everything. Layers that were inches thick at the surface become paper thin a mile down. You need microscopes and chemical analysis to distinguish them. But they are still there. Annual records going back beyond the dawn of any human civilization into a time when the world was fundamentally different. As snow falls and compresses into ice, tiny air bubbles get sealed inside. These bubbles are time capsules containing samples of the atmosphere exactly as it existed when that snow fell. Scientists can extract these bubbles and measure their contents: carbon dioxide levels, methane concentrations, trace gases that exist in parts per billion. When Alexa drills an ice core from Greenland, she's not just collecting frozen water. She's collecting bottled atmosphere from 12,800 years ago. The Younger Dryas shows up in these cores like a scar. Methane levels plummet right at the boundary layer, dropping by about 30% within decades. This tells scientists something important. Methane comes primarily from wetlands, where organic matter decomposes in waterlogged conditions. When methane levels crash, it means wetlands around the world were drying up or freezing simultaneously. The planet was getting colder and drier at the same time. But ice cores reveal something even more precise than gas concentrations. They reveal temperature itself, recorded in the ratio of oxygen isotopes in the ice. Water molecules come in different weights depending on which isotopes of oxygen they contain. When ocean water evaporates, lighter molecules evaporate more easily than heavier ones. The ratio between these isotopes in ice depends on how cold it was when the snow fell. Scientists can measure these ratios with extraordinary precision, essentially reading past temperatures directly from the chemistry of the ice. The Younger Dryas boundary layer shows isotope ratios shifting dramatically over the course of just a few years' worth of snowfall. Not gradually, not ambiguously. Something made temperatures plummet faster than the known physics of the climate system should allow. Alexa remembers the first time she saw the Younger Dryas boundary in a core she had drilled herself. She had been told what to expect: the sharp shift in the isotope ratios, the change in the dust concentrations, the chemical signature of a climate system that had snapped into a different mode. But knowing what to expect and seeing it are different things. The layer is thin, a few centimeters. On either side of it, the ice tells a coherent story, warming or cooling gradually as you would expect. And then this line, this almost geometrically precise transition, as if the climate had simply decided to be different and had been different from the following season onward. She has looked at a great many ice cores in 15 years. None of them have shaken her quite like that line. Ice cores are not the only record. Ocean floor sediment cores, lake sediment cores, tree rings, cave formations called speleothems. Every independent archive points to the same event at the same time. In the North Atlantic, ocean sediment layers show that cold water species of tiny marine organisms suddenly replace warm water species right at the Younger Dryas boundary. Lake cores across Europe, North America and Asia all show the same pattern. Forest pollen declining dramatically, tundra plants returning. Tree rings show dramatic changes in growth patterns. Wide rings indicating good conditions suddenly becoming narrow. The signature of trees struggling to survive in deteriorating climate. Then there is the black mat. Across North America, archaeologists kept finding a thin, dark layer in sediments dated to the Younger Dryas boundary. Sometimes just a few centimeters thick, sometimes spread across hundreds of square miles. It contains charcoal, suggesting widespread fires. It contains unusual concentrations of iridium and platinum, elements rare in Earth's crust but common in asteroids. It contains microscopic spherules, tiny beads of once molten material, and it contains nanodiamonds, crystals that only form under extreme heat and pressure. Not everyone agrees on what the black mat means, but everyone agrees it exists. and everyone agrees it dates to the Younger Dryas boundary. The debate is not about the evidence, it is about interpretation. For many climate scientists, the most compelling explanation for the Younger Dryas does not involve comets or volcanoes. It involves water, specifically an inland sea that once covered the center of North America and whose sudden drainage may have shut down the ocean circulation system that keeps the North Atlantic, and everything that depends on it, warm. At the end of the last ice age, the northern half of North America was dominated by the Laurentide ice sheet, a wall of frozen water in some places 2 miles thick. South of this ice, meltwater pooled into lakes. One of those lakes was Lake Agassiz, and calling it a lake is almost an insult to its scale. At its maximum, it covered an area larger than all 5 of the modern Great Lakes combined, stretching across what is now Manitoba, Saskatchewan, Ontario, North Dakota, and Minnesota. An inland sea, held in place by ice and low land, filling year after year as the glaciers continued to melt. The only thing keeping all that water from surging into the ocean was the Laurentide ice sheet itself, acting as a giant plug. As the ice thinned and retreated, parts of its margin became unstable. Channels formed, pressure built behind natural barriers. At some point, a critical threshold was crossed. An ice dam gave way, or a low drainage divide was overtopped, and an unimaginable volume of fresh water burst into the ocean, possibly in a matter of years, possibly even faster. Enough fresh water to raise global sea levels by several meters. To understand why this matters, you need to think about the ocean not as a static blue backdrop, but as a moving machine. Warm, salty water flows northward from the tropics along the surface of the Atlantic. You can feel one of its branches as the Gulf Stream, bringing surprisingly mild conditions to northern Europe. As this water travels north, it cools. When water cools, it becomes denser. When it becomes denser, it sinks, plunging to the deep ocean and flowing back southward as a cold undercurrent. That sinking is crucial. It draws warm water north, dumps heat into the atmosphere, and keeps the circulation running. As long as the pump works, Northern Europe and the North Atlantic stay much warmer than their latitude alone would suggest. But the pump has a weakness. It relies on the surface water being both cold and salty, dense enough to sink. Pouring an enormous pulse of fresh water into the North Atlantic is like adding a bucket of fresh water to a saltwater tank. You dilute it. You make it lighter. If the surface waters become too fresh, they stop sinking efficiently. The conveyor belt weakens. In some model simulations, it can collapse entirely for centuries. This is the Lake Agassiz hypothesis. The catastrophic drainage of glacial lakes in North America suddenly flooded the North Atlantic with fresh water. The overturning circulation faltered, and the northward transport of tropical heat was sharply reduced. Take away that oceanic heat delivery and the climate responds quickly. Europe and the North Atlantic cool first and hardest. Sea ice expands. Snow from winter lingers longer into spring. Brighter, whiter surfaces reflect more sunlight back into space, reinforcing the cooling. Storm tracks shift. Precipitation patterns rearrange. Within a human lifetime or two, regions that had been on a pleasant path out of the Ice Age are pushed back toward glacial conditions. Thomas has spent his career building and testing models of exactly this process, and he finds it physically plausible in a way that many other hypotheses are not. The physics are known. The mechanism is real. The question is whether the evidence supports the specific sequence of events at the specific moment of the Younger Dryas onset. And here the story gets complicated. The Lake Agassiz hypothesis is the leading explanation, but it is not the settled explanation. The route the floodwaters actually took is still debated. Early versions imagined a dramatic drainage eastward through the Great Lakes and out the St. Lawrence directly into the North Atlantic. But later work suggested the topography may have favoured a different route, northward through what is now the Mackenzie River system into the Arctic Ocean. The timing is contested. The magnitude of the pulse required to significantly weaken the overturning circulation is uncertain. Thomas is the first to admit that his favourite explanation has unresolved problems. The Lake Agassiz hypothesis is where many scientists start when thinking about the Younger Dryas. It is not where the conversation ends. In 2007, a group of researchers proposed a dramatic alternative explanation for the Younger Dryas. They suggested that around 12,800 years ago, just as the world was easing out of the Ice Age, Earth was struck, not by a single massive object like the asteroid that killed the dinosaurs, but by a fragmented comet or swarm of space debris. The impacts or airbursts happened largely over the Laurentide ice sheet. They called it the Younger Dryas impact hypothesis. From the moment it was published, it was controversial. In their picture, a comet that has been silently orbiting the Sun for millions of years drifts into a fatal path. As it approaches Earth, it cracks into pieces. Instead of a single crater-forming blow, you get a pattern of fire from the sky. Some fragments slam directly into the ice. Others explode as air bursts, like the 1908 Tunguska event in Siberia, but on a much larger scale. Each blast releases energy comparable to multiple nuclear weapons, vaporizing ice and rock, igniting forests, flinging debris into the upper atmosphere. The fingerprints of this catastrophe, the researchers argued, are preserved in a thin boundary layer across multiple continents. In that layer they reported nanodiamonds, crystals so small they are measured in billionths of a meter, found at concentrations far higher than in the sediments above and below. Magnetic microspherules, tiny glassy metallic beads rich in iron, created when rock and soil are flash melted by extreme heat. High-temperature melt glass, formed at temperatures well above those reached in normal wildfires. Elevated concentrations of iridium and platinum, elements more common in meteorites than in Earth's crust, spiking right at the Younger Dryas boundary. Put together, the researchers argued, these features pointed to a cosmic origin. The implications for climate would be enormous. An impact or series of airbursts over an ice sheet does not just scar the surface. It vaporizes ice, melts huge volumes almost instantly, and lofts dust, soot, and water vapor high into the atmosphere. Forests in the blast zone ignite, feeding continent-scale wildfires. Smoke and ash spread across the northern hemisphere, dimming sunlight and cooling the surface. In this view, the cosmic event and the meltwater hypothesis are not competing explanations. They are linked. The explosions trigger the floods. The floods disrupt the ocean circulation. Fire from the sky becomes the switch that starts the chain. From the very beginning, the hypothesis attracted fierce disagreement. Some researchers found similar signals in their own samples from boundary layer sites. Others looked and found nothing unusual. Disagreements emerged over methods. How exactly do you identify a nanodiamond under an electron microscope? How do you distinguish an impact microspheral from the products of ordinary fires, volcanoes, or modern industrial pollution? For the dinosaur extinction, the case rests on multiple independent lines, all converging on a single massive crater at just the right age. For the Younger Dryas, the picture has remained fuzzier. Some studies report clear peaks in platinum and impact-associated materials. Others sample nearby and find nothing. Then in 2018, a discovery beneath the Greenland ice sheet poured new fuel on the debate. Radar surveys revealed a circular depression roughly 31 kilometers across, large enough to count as a true giant among craters. It was named Hiawatha. On maps of Greenland's bedrock, it looks disturbingly like the scar an impact would leave beneath an ice sheet. For a moment, it seemed as though the hypothesis had found its smoking gun. But the key question is timing. Dating a structure buried under a kilometre of ice is not straightforward, and subsequent work has tended to push Hiawatha's age older, possibly hundreds of thousands or even millions of years before the Younger Dryas. If that is right, it cannot be the cause. It may represent an earlier, unrelated catastrophe, preserved under Greenland's ice while the world's other craters slowly eroded away. The impact hypothesis sits in a peculiar position in the scientific literature. It refuses to go away, because too much data hints at something unusual in that thin boundary layer. But it also refuses to settle into consensus, because the evidence is contested at almost every point. Devora has her own view of the hypothesis, shaped by years of working in the archaeological record. What she finds compelling is not the nanodiamonds or the microspherules. She leaves that to the geologists, but the timing. Something happened at the Younger Dryas boundary that left a mark on human communities across multiple continents, almost simultaneously. Whether that something was cosmic or terrestrial or both, she does not yet know. But she knows it was real, and she knows it was sudden. The first thing you would notice if you could stand in late Ice Age North America is the sound. Before the Younger Dryas, this was not quiet tundra and scattered pine. It was loud. Wind over grasslands, hooves thundering, tusks cracking ice. The low rumble of herds so large they seemed to pull the horizon along with them. Woolly mammoths in herds of thousands, mastodons moving through the forests, American horses and camels picking their way between patches of snow and grass, giant ground sloths, some as tall as a small house, covered in thick fur, claws like scythes, saber-toothed cats with canines longer than your hand, dire wolves, American lions, short-faced bears. Then, over a geologically brief moment, that sound began to fade. By the end of the Younger Dryas, North America's megafauna had been gutted. Roughly 35 genera of large mammals disappeared. Not just a few species here and there, but whole branches of the ecological family tree. Mammoths, mastodons, giant ground sloths, American lions, short-faced bears, saber-toothed cats, the native horses and camels, the massive beavers. South America lost many of its giants as well. Europe and Asia saw fewer total extinctions, but still significant ones. Woolly rhinoceroses, straight-tusked elephants, some large deer and bison lineages. The timing of this die-off lines up eerily with the onset of Younger Dryas cooling around 12,800 years ago. The arguments about what caused the extinctions are as unresolved as the arguments about what caused the Younger Dryas itself. and the two questions are closely entangled. One camp points to climate. Megafauna are often specialists evolved under specific conditions. The transition out of the Ice Age was not a smooth ramp. It was a series of sharp steps and wobbles. Forests advanced, retreated, and reorganized. The sudden Younger Dryas cold snap could have fragmented already stressed habitats, breaking migration routes, cutting off winter forage, pushing populations already near their limit over the edge. Another camp points to humans. By the time the Younger Dryas hit, people had spread across the Americas. The overkill hypothesis argues that small but highly efficient bands of hunters, armed with advanced projectiles and coordinated strategies, moved into ecosystems where large animals had no evolutionary experience with such predators. Even modest hunting pressure could have rapidly reduced populations of animals that reproduce slowly. Mammoths and mastodons take many years to mature and produce few offspring. Under this argument, the giants were not killed by cold. They were eaten out of existence, and the Younger Dryas was irrelevant or secondary to the human pressure that was already building. A third view, which has gained ground in recent years, combines both explanations. Climate change alters vegetation and reduces carrying capacity. Populations shrink and become fragmented. Into this vulnerable system, human hunters arrive. Even low-level hunting applied to already stressed herds can tip the scales. Disease, perhaps moving with humans or their dogs, may have played a role as well. Under this combined pressure model, the megafauna were living on the edge, and the Younger Dryas was the last shove. What is particularly telling is that just as the megafauna vanish, Clovis culture vanishes with them. At the Younger Dryas boundary, the classic fluted points and the broader toolkit associated with them disappear from the archaeological record, replaced by a patchwork of regional traditions with different spear point styles and different hunting strategies. This does not mean the people disappeared, it means their world did. If your entire way of life is built around hunting mammoths on open plains, a sudden loss of mammoths is an existential crisis. Hunting strategies must change. Territories shift. Trade networks and social alliances reorganize. The extinction of the giants forced a cultural extinction and rebirth. The end of Clovis and the rise of something new, more fragmented, more locally adapted to a world that had become fundamentally quieter. When the big animals went quiet, the humans did not. They could not. Silence for them would have meant extinction. On the North American plains, the people we call Clovis had once lived in a world tuned to mammoth rhythms. Their tools, their stories, their migrations, their social bonds, everything was wrapped around following herds, turning ivory and bone and hide into shelter, clothing, and status. Then, right at the Younger Dryas boundary, the mammoths thin out, and almost in lockstep, so do the classic Clovis artifacts. Below a certain layer in the soil, fluted points, long-distance trade in high-quality stone, big game kill sites. Above it, different shapes, different hunting strategies, different sites. Not a single unified culture blanketing half a continent, but a patchwork quilt of local traditions adapting to a quieter, more fragmented landscape. Across the ocean, in the hills and valleys of the eastern Mediterranean, another experiment in human living is underway when the cold returns. The Natufian people, the ones Devora has spent her career studying, are some of the first we know of who tried something like settled life before farming. Before the Younger Dryas, they cluster in stone-built hamlets, some occupied for generations, harvesting wild cereals and building what looks, from a distance, almost like a preview of village life. Then the Younger Dryas arrives, and the Levantine climate flicks back toward arid. Rainfall declines. The stands of wild cereals that once grew thick and predictable become patchy and unreliable. Lakes that had been full for generations begin to dry. Devora excavates a site from this exact period, and the evidence is extraordinary in its specificity. The abandonment is not gradual. You can see it in a single stratigraphic layer, a horizon of ash and wind-blown dust that sits between the occupation levels below and the changed assemblage above. Below the layer, plastered floors, storage pits, the grinding stones that speak of a community processing grain regularly and with confidence. Above, a different pattern, the tools of a more mobile existence, the grinding stones gone. Something happened at this site, at this moment, that ended one way of life and began another. Devora believes the Younger Dryas is what happened. But the crisis did not produce only retreat. In some places and among some communities, the disruption of reliable wild food sources appears to have pushed people towards something new. Grain becomes more central in the archaeological record of later Natufian sites. Grinding stones multiply. Plant remains start to show physical changes. Thicker seed coats, non-shattering stalks that hint at human selection. Fields that once belonged entirely to the wind being nudged, season by season, into something else. Agriculture, in this telling, is not a triumphant invention. It is a negotiated truce with uncertainty. If you protect us from random failure, we will protect you from random death. Move a bit north and east onto the limestone plateau of southeastern Turkey, and another kind of response to crisis rises out of the rock. Göbekli Tepe does not look like something you build when times are easy. Right at the transition out of the Younger Dryas, around 11,600 years ago, people in this region begin carving and raising enormous T-shaped stone pillars, some weighing more than 50 tons. They set them in circles and ovals, decorate them with animals and abstract symbols whose meanings we can only guess, and invest staggering amounts of organized labor in a place that appears to have been a ritual center, visited seasonally perhaps for feasts or ceremonies tied to the turning of years. And as far as we can tell, the people who built it were still hunter-gatherers. No cities, no writing, no metal. Just stone, organization, and an apparent need to build something that would outlast them. Why then? Why there? No one knows for certain. But the timing is arresting. The oldest levels of Göbekli Tepe fall just after the Younger Dryas's end, a few centuries after generations had endured drought, abrupt cold, and shifting resources. Some researchers see the site as a monument to survival, a stone testament built by people whose grandparents had grown up in a harsher world and watched it suddenly, disorientingly, warm. Others suggest it could be a response to instability itself, a way to bind scattered groups together in shared myth and ritual, to coordinate labor and exchange in a world where climate had recently shown itself to be unpredictable and dangerous. When nature stops feeling reliable, you might start trying to anchor meaning in objects that will outlast you. Pillars sunk into bedrock, stories etched into stone. The Lake Agassiz meltwater hypothesis and the cosmic impact hypothesis are the two most discussed explanations for the Younger Dryas. But they are not the only candidates. The climate system is not a simple machine with a single off switch, and some researchers have increasingly come to think that the Younger Dryas may have been the result not of one dramatic trigger, but of several smaller influences arriving in unfortunate synchrony. Consider the volcano. About 12,900 years ago, right on the doorstep of the Younger Dryas, an explosive eruption tore open the ground in what is now Western Germany. Today we call it the Lacher Sea eruption, named after the lake that fills its crater. At the time, it would have been an almost incomprehensible spectacle. Columns of ash punching into the stratosphere, pyroclastic flows racing down valleys, forests flattened under blankets of pumice. Volcanoes like this do not just blacken the local sky. They pump sulfur into the upper atmosphere, where it forms tiny droplets that scatter sunlight back into space. After the Tambora eruption of 1815, the following year was called the Year Without a Summer, so it is tempting to look at Lacher Sea and imagine a similar script, a veil of volcanic aerosols providing the first nudge that tipped an already fragile climate toward a deeper, longer cold phase. But close is not exact. The Lacher Sea eruption appears to precede the sharp temperature drop by enough time that many researchers see it as a prelude rather than the main cause, and the atmospheric effects of even a large eruption typically last a few years to a decade, not 1,200 years. Volcanoes may have contributed, may have weakened the system at a critical moment, but they struggle to explain the duration of the Younger Dryas on their own. Then there is the sun. Our star is not a perfectly steady lamp. Its output wobbles over time in cycles of about 11 years and longer, waxing and waning in ways we still do not fully understand. In the Greenland ice, scientists measure the concentration of a rare isotope called beryllium-10, produced when cosmic rays slam into air molecules in the upper atmosphere. When the sun is active, its magnetic field shields Earth from cosmic rays and beryllium-10 production drops. When the sun is quiet, the opposite happens. Parts of the Younger Dryas, when read through this beryllium-10 record, look like a time when the sun went into one of its quieter moods. Solar output may have dipped at precisely the wrong moment. A slightly fainter sun does not sound dramatic. But imagine combining that dimming with fresh cold meltwater, flooding into the Atlantic, a disrupted ocean conveyor, and a volcanic veil over Europe. The surface of the North Atlantic cools. Sea ice spreads a little farther each winter. Snow lingers into spring. A brighter, whiter planet reflects more sunlight back into space. Under those conditions, the climate system does not need a huge shove. It just needs one more small, well-timed push, and it may lurch into a new, colder pattern all on its own. This is where the idea of cascading causes becomes hard to avoid. Instead of hunting for one single culprit, some researchers now picture the Younger Dryas as the result of a pileup. A cooling sun, restless ice sheets, a jittery Atlantic overturning circulation, occasional explosive eruptions. Each factor on its own might have produced only modest bumps and dips. Together, they may have synchronized into a perfect storm, locking the northern hemisphere into a deep chill. Tomas finds this picture both intellectually compelling and professionally uncomfortable. It is compelling because it fits the messy, multifactorial nature of real climate events. It is uncomfortable because a multifactorial explanation is harder to test, harder to model, harder to confirm or refute. The Younger Dryas in this framing may not have a single cause. It may have had a chorus of them. If the beginning of the Younger Dryas feels like someone flipped a switch, The end feels like they snapped the breaker. About 11,600 years ago, in the ice high above what is now Greenland, something changed with terrifying speed. In the layers of snow that were falling then, later compacted into ice, you can see it as clearly as if a thermometer had been frozen in place. 1 year, the isotopes tell us, the air above the ice was brutally cold. Younger Dryas cold. Within what may have been just a few years, possibly even less, temperatures had jumped by around 10 degrees Celsius. On human scales, that is like stepping out of late February into late May between one lifetime and the next. On geological scales, it is a lightning strike. In the Greenland ice cores, the transition looks almost like a knife edge. For more than 1,000 years, the layers build up with the signature of a frigid, unstable climate. Heavy isotopes whispering cold, dust hinting at dry winds and sparse vegetation, trapped bubbles holding lower greenhouse gas levels. Then abruptly the pattern shifts. Isotope ratios swing toward values that mean warmth. Dust concentrations drop. Methane rises. It is as if the ice is telling you in a few thin layers that the world outside has stepped into a different state. What could make an entire climate regime, anchored by ice sheets, ocean currents, and atmospheric circulation, give way so quickly? The leading suspect is the same system that may have helped trigger the cold in the first place, the Atlantic meridional overturning circulation. In many models, once the flow is weakened by freshwater input, it can settle into a sluggish, cold-favouring pattern. But that state is not necessarily permanent. As ice sheets shrink, as meltwater pulses slow, as the salinity and temperature pattern shifts, the system can creep back toward a threshold. Cross that threshold, and the overturning can suddenly strengthen again, hauling heat northward with surprising speed. The oceans were not acting alone. While the Younger Dryas played out, Earth was still sliding along its long, slow orbital cycles, the Milankovitch rhythms that subtly alter how sunlight is distributed across the planet. By about 11,600 years ago, the Northern Hemisphere's summer insolation had been rising for some time, pushing steadily against the Younger Dryas cold from behind, like a steady hand on the back of a locked door. At some point, the combination of stronger summer sun, shrinking ice sheets, and a gradually shifting ocean may have crossed a critical line. Feedbacks that had favoured ice and cold flipped direction. Greenhouse gases that had been creeping upward began to amplify the warming, and the climate system, which had held its cold Younger Dryas pattern for 1,200 years, let go. Alexa has looked at the termination of the Younger Dryas in cores many times, and she always comes back to the same feeling. The speed of it is as unsettling as the onset. We are not accustomed, she says, to thinking of large, complex systems as capable of this kind of behaviour. 1,000 years of stability, and then, within a decade, something completely different. The climate system is not a thermostat that adjusts smoothly. It is more like a system that can hold a position for a very long time, and then release all of its accumulated tension at once. The way a fault line holds for centuries and then moves in seconds. The Younger Dryas is a demonstration of that capacity. Both its onset and its end are demonstrations. The system can snap. If the Younger Dryas were only an ancient story, it might be merely fascinating. But the reason it still pulls at scientists and keeps appearing in modern climate discussions is that it does not feel entirely finished. It feels in some ways like a rehearsal, because the main suspect in that ancient drama the Atlantic Meridional Overturning Circulation, the great ocean conveyor that helps steer the Younger Dryas into being, is not just a concept in a textbook. It is a living system still humming beneath the surface of the Atlantic, still carrying heat northward, and today it is measurably slowing down. As Greenland's ice melts under modern warming, as Arctic sea ice thins and northern rivers pour more fresh water into the ocean, the surface waters of the North Atlantic are becoming less salty in places, less dense, less eager to sink. All the ingredients that in models and in the paleoclimate record can weaken the overturning circulation are quietly accumulating again. Nobody is claiming that tomorrow we wake up in another Younger Dryas. The world now is different. Greenhouse gas levels are far higher. The background state of the climate is warmer. The ice sheets are smaller. But the physics of density, salt, and sinking water have not changed. Oceanographers are watching the AMOC like you might watch a sleeping giant whose breathing has become a little shallower. The Younger Dryas also carries a lesson about tipping points that has become increasingly central to how climate scientists think about the future. For a long time, it was easy to imagine Earth's climate as basically gradualist. Temperatures creeping up or down over tens of thousands of years, changes real and sometimes dramatic but buffered by long time scales. The Younger Dryas shows that this picture is incomplete. Complex systems, from ecosystems to ocean circulation to financial markets, can absorb stress for a long time and then, beyond some hidden threshold, flip. The change is not announced. No alarm sounds over the North Atlantic when the overturning circulation reorganizes, but the system's internal feedbacks quietly switch direction, and what once resisted change now amplifies it. Climate models are the main tools we have for looking into the future, and the Younger Dryas functions as one of their most demanding exam questions. If a model, when fed the right boundary conditions, ice sheet sizes, orbital settings, greenhouse gas levels, cannot produce anything like the Younger Dryas, that is a red flag. It suggests the model may be missing some crucial feedback, some way that ocean and ice and atmosphere can gang up to produce abrupt change. When a model can realistically simulate both the onset and the termination of the Younger Dryas, matching the timing and magnitude of the temperature changes seen in the ice cores and sediments, confidence grows that it might be able to handle whatever is coming next. There is a softer echo as well, harder to quantify but difficult to ignore. Across cultures scattered around the world, there are flood myths, tales of waters rising suddenly, engulfing valleys and lowlands, forcing people into boats or onto mountain refuges. In Mesopotamia, the story of Utnapishtim in the Epic of Gilgamesh. In Hindu traditions, Manu warned by a fish of a coming deluge. Among many indigenous American nations, narratives of great floods and worlds remade. Most historians treat these as cultural motifs, shaped and reshaped across millennia, not as direct eyewitness accounts of a single event. Yet some researchers wonder if behind the shared pattern there might be fragments of real experience. Abrupt sea level jumps as glacial lakes drained, river courses transformed by meltwater floods, coastlines drowned as the last ice retreated. The line between geology and memory is thin in deep time, and human beings are storytelling animals. When the world lurches, we do not only adapt physically, we narrate. We encode shock and survival, into tales that last longer than any one village. Tomas does not work on flood myths. He is a physical oceanographer, and he is careful about what kinds of claims his discipline can support. But he has thought about the Younger Dryas long enough that he has developed a kind of personal relationship with it. The way you develop a relationship with a problem you've been trying to solve for 20 years and have not quite solved. What it has given him, more than any specific result, is a particular kind of humility about the stability of the world. Everything we think of as normal, everything we have built our civilizations around, has happened within a very specific climatic window. The Younger Dryas is what sits just outside that window. It is what the world looks like when the conveyor stumbles. The Younger Dryas refuses to sit still as a solved mystery. Each new core, each new data set nudges the balance between theories, but never quite locks one in place. Maybe the meltwater from Lake Agassiz mattered more than we currently think. Maybe an impact did strike somewhere we've not yet found the crater. Maybe multiple triggers overlapped in ways our models are only beginning to grasp. It is entirely possible that we will never have a single tidy answer, that the Younger Dryas was, like most of the important things that happen in complex systems, the product of a confluence rather than a cause. There is a quiet beauty in that. Somewhere under the Greenland ice in layers thinner than a sheet of paper, that sudden winter is still recorded as tiny shifts in trapped air and snow crystals. Somewhere on the ocean floor, in grains of sand and shells of microscopic plankton, the same story lies written in a different script. The planet is remembering itself, and we're slowly learning to read the memory. Alexa is back in Greenland again next summer. She has a new section of core she's been waiting to analyze, pulled from a depth that corresponds to the Younger Dryas boundary, in a location that has not been drilled before. She does not know what it will show. She suspects it will confirm what the other cores have shown, but she also suspects, from experience, that it will show her at least one thing she did not expect. The Younger Dryas has been surprising scientists since the day it was discovered. She sees no reason to expect that to stop. Devora will continue excavating her Natufian site for at least 2 more seasons. The stratigraphic layer she found, the horizon of ash and wind-blown dust that sits between the occupation levels, has given her more questions than answers, which is exactly how she likes it. She wants to know what the people who lived there did in the years immediately after the abandonment. Did they come back? Did they go somewhere else and start again? The answer, she is increasingly sure, is preserved in the layers just above the layer she has been studying. She just has to get there. Tomas is working on a paper. He's been working on it for longer than he would like to admit. It is about the possibility that the Younger Dryas involved not one but 2 distinct phases of weakened overturning circulation, separated by a partial recovery, and that this double-dip structure explains some of the regional variability in the climate record that single-event models struggle to account for. He is not sure the paper is right. He is fairly sure it is interesting. In the Younger Dryas literature, interesting is enough to keep a conversation going for another decade. The world that emerged from the Younger Dryas was not just warmer. It was unusually stable, and that stability, as secure as it can feel when you're born into it, is not guaranteed. We are children of a stable interval, telling stories under a sky that has seen far stranger years. The ice remembers those years. Every season more of that memory is being read, and above the Atlantic the same winds still blow. In the deep ocean the same currents still turn. The mystery will still be there in the morning. This has been Midnight Chronicle. Sleep well wherever in the world you are tonight.